Okay, welcome back, guys. This is the last model that we'll see in our discussion on advanced selection. So we have talked about task allocation and then price discrimination, and now we'll talk about an auction. So what is auction? You probably have seen auctions in movies or in TV or in novels or in person. Maybe some of you have experienced auction in person. And in an auction, a seller sells an individual good to multiple potential buyers. This can be different in different auctions, but in the situation that we are considering is this. One seller is selling an individual good like a house or a painting to multiple potential buyers. Actually, there will be two buyers. And in contrast to the previous setup, the model of price discrimination, the seller cannot produce the good without any limitation. In other words, there is limitation in supply. For example, there are limited number of Picasso paintings, and probably the number of buyers who wants to buy Picasso paintings is larger than the number of available Picasso paintings. So in that case, these buyers have to compete to buy these limitedly available Picasso paintings. Another example is real estate. Obviously, the land is huge, but not two lands are exactly the same. So every piece of land is different, right? In location or in whatever aspect, they are all different. So in that sense, the real estate is with limited availability, and also the earth is huge and land is huge, but the supply is limited. And another example is telecommunication spectrum. Telecommunication companies have to use different spectrums to avoid interference. So the availability of a spectrum is limited. So in that case, we use auction to allocate the spectrums to different telecommunication companies. Okay, and probably you have heard of these auctions like the standard auction, English auction, or Dutch auction. English auction is sometimes called ascending price auction because it starts the price starts very low and it increases. So it's ascending price. So in an English auction, each buyer at any stage of the auction can announce a price offer that is higher than the previously announced bid, or the auctioneer just increase the price and each buyer just raise a panel to show that I'm willing to pay that price. And if everybody but just one buyer drops, then the buyer who let's say survives buy the good. Okay, so that's how English auction works, right? So probably you have seen that kind of situation in the movie. So this is probably the most commonly used auction in reality. Dutch auction is very similar, but it's called descending price auction for a reason, because the price starts very high and it decreases. And so it works like this. The auctioneer starts by calling a very large price and continuously lower the price, and the price until a buyer accepts the price. So in contrast to English auction, Dutch auction is a descending price auction because the price decreases over time. And if just one buyer accepts the price, then the auction is over at that point and the buyer pays the price. Okay, so these are two typical auctions, and in economics we also consider these auctions as well. Very commonly Vickrey auction, which is also known as the second price sealed bid auction or second price auction for short. In Vickrey auction, buyers simultaneously submit a price in a sealed envelope, and the good is sold to the buyer with the highest bid at the second highest price. That's why it's called second price auction. So the winner is the one who submit the highest bid, but the price that the buyer has to pay is the second highest price. So this sounds somewhat weird, but this is actually very intuitive, and it has very good property. And the last one is the first price sealed bid auction, or first price auction for short. In first price auction, buyers simultaneously submit a price in a sealed envelope, which is the same as in victory auction, and the good is sold to the buyer with the highest bid at the highest price offer. So you bid like 100, and if you wins, then you pay 100, whatever unit of the currency is. So this one sounds more intuitive, right? So you pay what you submit, right? So the first price auction sounds more intuitive, but it has some limitation. It has some drawbacks. But victory auction is very nice in terms of incentive. So in victory auction, truthful revelation is incentive compatible. In other words, it is the best response to any strategy to report your type, your willingness to pay truthfully. That is the best response, and that is the equilibrium strategy. That's actually dominant strategy. Regardless of the bids or the strategies of the other players, you just report your maximum willingness to pay. So that's the dominant strategy. That is equilibrium strategy. So victory auction has very nice property, which is that the buyers has to report they want to report their own maximum willingness to pay, and no one has the incentive to deviate from that. So that's an equilibrium strategy. So that's very nice. And also, at first it sounds weird, but if you look at it very closely, you can realize that this victory auction is actually the same to English auction, the ascending price auction, in terms of strategy. So victory auction and English auction are strategically equivalent. And also the Dutch auction, the descending price auction, the Dutch auction is strategically equivalent to the first price auction. So the second price auction is basically the same with the English auction, and the first price auction is basically the same with the Dutch auction. If you have time, we can talk about this in more detail, but probably, not now. We can talk about this later if you have time. In this lecture, I just want to focus on the very abstract setting, and we'll see that the lesson that we saw in price discrimination or task allocation is repeated here. So what was that? So if there is some asymmetric information problem about type, in other words, if there is adverse selection problem, then the auctioneer or the seller wants to distort the value of the lower value transaction. So in price discrimination, like in economy class in airplane, the lower value transactions are distorted. So it's not provided at the efficient level. The value of it is discounted, is distorted. That's how we maximize the profit. To maximize the profit, you want to lower the value of low value transaction. By doing so, you can prevent the high type from deviating to the low type option. So that was the lesson that the repeated lesson that we saw in test collocation and in price discrimination, and you'll see the same thing here in the setup of in the model of auction. Okay, so this is the model. So there is one seller who is selling an indivisible good, let's say a house, to two risk-neutral potential buyers. Okay, so in previous model, I mean the model of price discrimination, we didn't talk about the number of buyers because we just assumed there are infinitely many buyers. That was implicitly assumed in our previous discussion. So there was no limitation in supply in the model of price discrimination, but that's not the case here. Here there is only one good. Okay, there is only one unit of good, and so there is only one house, but there are two buyers. So these buyers are competing to buy this good, the house. Okay, and there is asymmetric information about the willingness to pay of the buyers. So there are two buyers, but the type of the buyer is private information, which means that I know my willingness to pay, but nobody else. So another buyer, the other buyer does not know my willingness to pay, and the seller does not know my willingness to pay. So the maximum willingness to pay, VI, is the private information that the buyer has, and this is basically the type of the buyer. Right? So the type of the buyer is VI, and VI is either VH or VL. So it is VH with probability P, and it is VL with probability 1 minus P. Okay, so this is basically the setup, and we'll think about a very general problem of auction design. Okay, so let's say that Xij is the probability that buyer I gets the good when Vi hat and Vj hat are announced. Okay, so Vi hat doesn't have to be the same with Vi. So you report that I'm type Vi hat. Okay, so it doesn't have to be the same with your real type. So this Vi hat and Vj hat are announced. In that case, buyer I who announced that I'm Vi hat type will get the good with probability Xij. So Xij is the probability that buyer I gets the good when Vi hat and Vj hat are announced. Okay. And similarly, we can define this Tij. So Tij is the price or the payment that the buyer I pays when Vi hat and Vj hat are announced. So first notice that the probability and the prices are functions of the announcement. Okay, and it's not just announcement of my type. Is the function of announcement of both buyers. Okay, so if I say I'm high type, the other buyer says I'm low type, then my probability that I get the good depends on my announcement and the other buyer's announcement. Okay, and also notice that this Tij may be positive even if I do not get the good. Okay, so this is not exactly the price. That's why I put this quotation mark on it. So Tij is price quotation mark that the buyer I has to pay, because maybe the buyer I has to pay something even if the buyer I doesn't get the good. Okay, that sounds somewhat weird, but if you think about some sort of participation fee, that may sound not so crazy, right? So maybe TIJ is just something including participation fee. Okay, so we just set this up and we focus on direct mechanism, which means each buyer announces their own type or some other type, and depending on the announcements, the allocation and the payments are made. So this is direct mechanism, and also we want to make it very, very general. So we want to allow everything. So like if one buyer announced that I'm low type and the other buyer announced that I'm high type, then maybe the low type buyer gets the good. Okay, maybe. I mean, that is allowed for now. But eventually we'll see that the high type buyer will get the good. But for now, we allow every possibility. The allocation is stochastic, I mean the probabilistic, so it doesn't have to be very deterministic. So if xij is either 0 or 1, then it is a deterministic mechanism, or it is a deterministic auction. So deterministic auction is included. We allow that. But we allow xij to be some fraction, so we will allow some stochastic allocation. Okay, so we start with very general setup. And here is the seller's problem. The seller's problem is to maximize the profit or the revenue. There is no production cost. You already have the house. You are just selling the house. So there is no production cost. You just maximize the expected revenue. Okay. So here, let's look at the objective function. There is 2 in front of the objective function. That means there are 2 buyers. And the expression in the square bracket is the expected revenue from 1 buyer. Okay. So the expected revenue from 1 buyer is expressed in the inside the square bracket. So let's look inside. So with probability P, the buyer is what? The high type buyer. Okay. So before we begin, the reason why we use this P to say that this is to represent the probability that the high type is announced is that we focus on direct mechanism, and we also want to characterize an incentive compatible mechanism, which means that we want to focus on truth telling, okay, truthful revelation. So in incentive compatible mechanism, truth telling is incentive compatible. So it is your best interest to report your type truthfully. So that's one property of incentive compatible mechanism, and we want to characterize that, because if a mechanism is not incentive compatible, then you don't know what's going to happen in this mechanism, right? So you probably will fail to achieve your goal, and probably some mess will be observed. So that's not what you want. So we want to characterize an incentive compatible mechanism, and that's why we use P as the probability that type H is announced. Okay, so with probability P, a buyer will be of high type, and in that case, with probability P again, the other buyer is also high type. In that case, this buyer will pay as much as THH. Okay, so what is THH? THH is the payment that a buyer has to pay when both buyers announce that I'm high type. Okay, and with probability 1 minus P, the other buyer is low type. So the buyer who announced that I'm high type will pay THL. Okay, THL is what? THL is the payment that the buyer who announces that I'm high type has to pay when one buyer announced that I'm high type, the other buyer announced that I'm low type. Okay, so that's the the payment that the buyer who announced that I'm high type is supposed to pay. And let's move on to the next. With probability 1 minus p, this buyer may be a low type, and then in that case, with probability p, the other buyer is of high type. So in that case, this low type buyer has to pay TLH. And with probability 1 minus p, the other buyer is also low type. In that case, this buyer has to pay TLL. Okay. Again, I want to emphasize that this has, for now, this has nothing to do with the allocation problem, the allocation of the house. So you may have to pay something even if you don't get the good. Okay, that is for now that is allowed. And if you maximize this revenue, to maximize revenue, you may have to figure out what is the best way to allocate the good. But that's the next story. For now, we just allow everything. So yeah, and we have bunch of constraints. Can you see how many constraints do we have? It looks like there are 4, but maybe there are more. The first one is what is that? The first one is the IR constraint. Okay, so it is participation constraint. So let's look at that expression. With probability p, the other buyer is high type, and my type is I. So I'm I type buyer, and the other buyer is with probability p, the other buyer is high type buyer. In that case, I get the good with probability XIH, and I pay TIH. Okay, and with probability 1 minus p, the other buyer is low type. In that case, I get the good with probability XIL, and I pay TIL. So that's the expected utility of buyer I, right? So that must be greater than or equal to 0. That means this buyer is not worse off by participating in this auction. So this is participation constraint, or the IR constraint. And the second set of constraints is the set of IC constraints, right? So on the left hand side, the expected utility of truthful revelation, and the right hand side you see the the expected utility of untruthful revelation. So if these constraints are satisfied, then the buyer is willing to reveal their type. Okay, so IC and IR constraints. So they are typical constraints, right? So the reason why we consider these constraints, these are necessary constraints, and these are the as we know, we want to characterize the optimal auction, right? But to characterize optimal auction, we need to consider this problem, right? So as I argued, as I showed in the previous lecture, this is one way to characterize the optimal auction. The other way is you consider all imaginable auctions, and you calculate the expected profits, and we compare the expected profits and pick the auction which gives the highest expected profit. That's the other way, but that is simply not possible, and our strategy is to focus on direct mechanism, and we just impose the minimal constraints and maximize the profit to characterize, to figure out what the optimal auction is. that's our strategy, right? So that's why we are considering this problem. So we have this IC and IR constraints, but we have more constraints at the bottom. So 2xii must be smaller than or equal to 1, and xij and xji must be smaller than or equal to 1. So what are these constraints? These constraints are called feasibility constraints. These constraints means that these xii or xij or xji, these are probabilities, right? So these cannot be larger than or equal to larger than 1, right? So the probabilities cannot be larger than 1. It cannot be smaller than 0. So, and because you have just one unit of good, one unit of a house, you cannot sell the good to two different people at the same time. So xii is the probability that buyer I gets the good when the announced types I and I, right? So let's say two buyers announce that I'm high type. In that case, the probability that the buyer gets the good cannot be larger than half, right? Again, let me repeat. So the probability that you get the good when both buyers announce that I'm high type cannot be greater than half. So that's the feasibility constraint. So that's the constraint that you see here. So 2 times xii must be smaller than or equal to 1. You can read the other constraint similarly. Xij and xji is smaller than or equal to 1. So what that means is one buyer announced that I'm high type, the other buyer announced that I'm low type. The probability that the sum of the probabilities that each buyer gets a good cannot be larger than 1 because you have only one unit of good. So that's why it's called feasibility constraint. Okay, so giving one indivisible good to two different people is not feasible. So we have to rule out that possibility. So that's why we have these feasibility constraints. Okay, so we have IC and IR constraints as we saw before. We have this now we have this feasibility constraints too. And the reason, one mathematical reason or mathematical effect of having this feasibility constraint is that it makes the problem solvable, or it makes it limits the problem so that the solution is solution exists. So let me go back to the objective function. There is no production cost. In contrast to the previous model, the model in the model of price discrimination, there was a production cost. So that limits the profits. Okay, so because there is production cost, the profit cannot be infinity. Okay, so you produce more, then the production cost increases. So that limits the profitability of selling this good. But here we don't have this production cost. Instead, we have this feasibility constraint. So that limits the profitability of selling. Okay, so you have just one good, so you cannot get infinity profit. Okay, let's move on to these definitions. So let's define TH equals to P times THH plus 1 minus P times THL. And similarly, we define TL equals P times TLH plus 1 minus P times TLL. So what are these? So TJ is the expected payment when this buyer declare type J. Okay, so if you declare that I'm high type, then your expected payment is TH. You expected to pay as much as TH. Okay, so or if you declare that you are low type, then you can expect that you will pay as much as TL. Okay, so you don't know the type of the other buyer, so you have to take an expectation. And similarly, we can define the probability like XH is P times XHH plus 1 minus P times XHL, and XL is P times XLH plus 1 minus P times XLL. Here, similarly, we can understand this Xj as the probability to get the good when this buyer declares that I'm type J. So if you declare that you are J type or the high type, let's say you declare that you are high type, then you get the good with probability XH. In XH, you see that the XHH is there and XHL is there, and you mix the probabilities. Okay, so we define these TH and TL and XH and XL to simplify the notation, and it helps the analysis a lot because of this. Let's look at the third bullet point. Then a buyer i's utility function, which looks kind of heavy, P times XJH times VI times TJH plus 1 minus P times XJL times VI minus TJL. So this is the utility function of the buyer I who announced that I'm type J. It can be written like this. It's simplified. It is simplified quite a lot. It can be written like Vi times Xj minus Tj. Okay, so using the notations that we just defined on the top, we can write down the utility function of buyer I like this: Vi times Xj minus Tj, which looks very similar to the expression at the bottom. So the expression at the bottom is the utility function that we used in the price discrimination model. Okay, in price discrimination model, the type was denoted by this theta, right? So theta I is the type of buyer I, and V was a concave function, which is function of Q, quality. So the V increases in quality. So if quality is high, then utility that you get from consuming it increases. And also you see at the last term, TJ, that's the payment, the total payment that you have to pay when you buy this good with quality QJ. Okay, so these two expressions looks very similar, right? Vi times Xj minus Tj looks very similar to theta I times V of Qj minus Tj. So V corresponds to theta, and X corresponds to V of Q, and T is T. So T, the payments are same. So what that means is this. It can be simple. The seller's problem can be simply written like this: 2 times P times TH plus 1 minus P times TL. So a buyer's expected payment, or the revenue from one buyer, is P times TH plus 1 minus P times TL. It can be read like this. So with probability P, the buyer will be high type. Because this is an incentive compatible mechanism, the buyer will announce that I'm high type, so the announcement will be truthful. In that case, TH will be earned from this buyer. And with probability 1 minus P, the buyer will be low type, and the buyer will announce that I'm low type. In that case, you can earn as much as TL from this buyer. So that's the expected revenue from one buyer, and because there are two buyers, we have 2 in front of it, but it doesn't matter. You can multiply 3 or 4 or 100. It doesn't matter. It doesn't change the result of it doesn't change the solution of this problem, right? As you know, the monotone transformation of objective function doesn't change the solution of the maximization problem, right? And we have these constraints. The first one is the IR constraint, right? So Vi times Xi minus Ti must be greater than or equal to 0. That means participating in this auction must be is better than not participating in this auction. So that's the IR constraint, or the participation constraint. And the second set of constraints is the set of IC constraints, right? The IC constraints requires that the revealing one's type truthfully is better than reporting one's type untruthfully. Okay, so Vi times Xi minus Ti must be greater than or equal to Vi times Xj minus Tj. And we have the feasibility constraints, right? So in total we have 7 constraints. We have 2 IR constraints for each type, and 2 IC constraints for each type, right? So we have 4, and then we have 3 feasibility constraints. So in total we have 7 constraints. Okay. And how do you solve this problem? Maybe we can stop here, or yeah, we can do a little bit more. Okay, how do you solve this problem? So this is a very the way we solve this problem is very similar to the way that we did before. We first figure out which constraints are binding, right? So let's first observe that the feasibility conditions do not say anything about the payment. So there is no T in the feasibility constraints. So it has nothing to do with the payment. So let's just ignore feasibility constraints for a moment, and we can show that the IRL and ICH constraints must be binding. So it's basically the same as before. So because the utility functions are basically the same as before, we can apply the same logic that we saw before to this problem. So it goes like this. First, we show that the IRH cannot be binding because the high type buyers participation constraint cannot be binding, because the if low type buyer is better off by participating in the auction, the one who has higher willingness to pay will be better off by participating in this auction, right? So if low type buyer participates, then of course high type buyer will participate. Okay, so the IRH cannot be binding. And then what? We take XH and XL as given for a moment and draw the constraints, the 3 constraints on this TH and TL space, and we figure out the area in which all 3 constraints are satisfied, and we draw ISO profit curve, and probably we have to push out the ISO profit curve as much as possible, and then you'll see that IRL and ICH must be binding. And if you are not sure about this, then go back to the lecture video of the price discrimination, and the logic is exactly the same. Okay, so IRL and ICH are binding. So at the bottom you see IRL, the binding IRL and ICH constraints. Okay, so because IRL is binding, TL can be written like VL times XL, and because ICH is binding, TH can be written like TL plus VH times XH minus VH times XL. And because using this binding IR constraint, we can eliminate TL from the binding IC constraint, and using this, we can rewrite the objective function, the profit function. Okay. So the next step is to see which of the feasibility constraints are binding. We differentiate the profit function with respect to the allocation probabilities XH and XL. So the profit function from one buyer looks like this: P times TH plus 1 minus P times TL. So this is the revenue or the profit from one buyer, expected revenue from one buyer. There are two buyers, so the expected profit is 2 times this revenue from one buyer, but because that doesn't change anything, so I just dropped 2. So let's just focus on this revenue from one buyer. Using the ICH constraint, I replace TH by VL times XL plus VH times XH minus VH times XL. So the expression in the square bracket is TH. And similarly, I replace TL by VL times XL. So in that, I use the IR constraint, binding IR constraint. So I eliminated all this payment T. We just have we just have the function of XH and XL. And so the next step is, as I said, I'm going to differentiate this with respect to XH and XL. But before doing that, let's look at this objective function for a moment. You may notice that this is a function of XH and XL, and it is linear in XH and XL, right? So what does that mean? So you cannot use the first order condition approach. The first order condition approach can be used only when the objective function is concave or convex, strictly concave or strictly convex in the choice variable. But here, the objective function is linear in the choice variables. What that means is we cannot use the first order condition approach, because if you differentiate this objective function with respect to XL or XH, it will be either just positive or negative. It will not be 0. You cannot find XH or XL which makes the first derivative equals to 0. So we cannot use the first order condition approach. So instead, we just want to look at, we just want to figure out whether we want to increase XH or we want to increase XL. So let's look at the second bullet point. So we differentiate this objective function, the profit function, with respect to XH. Then we get what? We get P times VH. So it is a positive number, right? So what that means is, if you increase XH, if you increase the allocation probability to high type buyer, then the profit increases. So you want to increase XH as much as possible, but there is limitation in it, right? The feasibility constraint. You cannot set the probability equals to 100, because it's a probability. Probability cannot be larger than 1. So that's the feasibility constraint. But if you increase XH, the profit increases. So you want to increase XH as much as possible. How do you know that? Because if you differentiate the profit function, the first derivative is P times VH, which is positive. That means if you increase XH slightly, then your profit increases as much as P times VH. No matter what XH is. So, if XH is large, or when XH is large or when XH is low, if you increase XH, your profit increases always. So you want to increase XH as much as possible. Okay, so that's how we figure out the optimal XH and optimal XL, and later we can figure out what optimal TH and TL are. Okay, and similarly, we differentiate the objective function with respect to XL. Then we get what? A somewhat complicated expression. So the reason is, as before, binding. The reason is the binding IC constraint. Because of the binding IC constraint, there is additional cost of increasing XL. The logic is pretty much same as before, so I don't want to repeat it, but just to refresh your memory, just briefly. So if you increase XL, then the high type buyer is drawn to the low type option more strongly than the low type buyer. So if XL increases and the high type buyer values this good a lot more than low type buyer, so if XL increases, then high type buyer may want to claim that I'm low type buyer, so the misreport may take place. Okay, so to prevent the high type buyer from misreporting one's type, you want to reduce XL. Okay, or you don't want to increase XL too much. Okay, so the first derivative is P times VL minus VH plus 1 minus P times VL. So obviously 1 minus P times VL is positive, so that's the revenue that you get from a low type buyer, but with probability P, the buyer will be high type. In that case, you lose something. Okay, so the revenue that you lose is the marginal revenue that you lose is VL minus VH or VH minus VL, whatever. So that's the additional cost that you have to pay. When you increase XL. All right. So as I said, you want to increase XH as much as possible, but XH is a complicated variable, so it has XHH and XHL inside. So you want to increase XH, you want to increase both variables as much as possible. So you want to increase XHH and you want to increase XHL. But there is feasibility constraint, so XHH cannot be larger than half. But you want to increase it as much as possible, so the conclusion is XHH must be half, 1 over 2, right? So XHH must be 1 over 2. And next, XHL. XHL plus XLH must be smaller than or equal to 1. And let's consider this situation. So one buyer claims that I'm high type. The other buyer claims that I'm low type. Then to whom you have to give the good? You have to give the good to the high type buyer. That's how you give an incentive to reveal one's type truthfully. So the high type buyer, the high type buyer's incentive compatibility constraint is binding, so you have to try to relax the incentive compatibility of the high type buyer. And to do that, when one buyer claims that I'm high type, the other buyer claims I am low type, you have to give the good to the high type buyer. Okay, that means XHL must be 1 and XLH must be 0. So we figure out three values, three optimal values. First, XHH must be half, and next XHL must be 1, and last XLH must be 0. Okay, so we figured out three values, the three optimal values of allocation probabilities, and last XLL is a bit complicated. So what we found before is this. Let's go back to the previous slide. So let's look at the expression at the bottom. So this may be positive or negative. So depending on the value of VH and VL and P, this value may be positive or negative. For example, if P is very small, what that means is the probability that the buyer is high type is low. That means the probability that the buyer is low type, which is 1 minus P, is high. In that case, you want to get the revenue from low type buyer. So you want to sell the good to the low type buyer. But if P is very large compared to 1 minus P, then you don't want to sell the goods. So there are only very small probability that the buyer is actually low type buyer, and you don't want to consider that. You just want to exclude this low type buyer. In that case, you don't want to sell the good to the low type buyer at all. Okay, so that's how it works. So you want to increase XL. So let's look at the second bullet point of this slide. So you increase XL if and only if this P times VL minus VH plus 1 minus P times VL is positive. Okay, for that you set XLL equals to half or 0. So you set XLL equals to half. What that means is if both buyers announce that I'm low type, then you sell the good to the low type buyer. Anyway, there are only low type buyers, so you have to sell the good. That will be optimal if P times VL minus VH plus 1 minus P times VL is positive. But you don't want to sell the good if that value is negative. So the meaning is, when both buyers announce that I'm low type, the good is traded if and only if this inequality holds. Okay. So in words, what that means is the seller prefers not to sell the product if the maximum willingness to pay of both buyers is too low, and the intuition is same as before, same as in the price discrimination case. The monopolist distorts the low value transaction in order to earn higher revenue from the high type buyer. Okay. So when there is this asymmetric information problem or the adverse selection problem, the seller or the auctioneer or the employer may want to distort some transactions. May want to lower the value of transaction. Okay. So in this case, if both buyers, in some cases, if both buyers announce that I'm low type, then you just don't sell the good. Okay. The trade is not taking place. So that's the distortion. that's obviously that's not optimal, but that's how you maximize the profit. So if there is asymmetric information problem and the seller wants to maximize the profit, then this will be the outcome. In some cases, the good will not be sold. Okay, so even if so one assumption that I didn't explicitly mentioned is that the seller doesn't care about this house. The seller doesn't enjoy any utility from having this house, by keeping this house. So the seller wants to sell the good, but in some situation, when there is this adverse selection problem, in some situation, the good is not traded, even though it is optimal, socially optimal to be traded. Okay, so that's the inefficiency that we observe. That's the inefficiency due to the adverse selection. Okay. Okay, so that's the end of the discussion on adverse selection. So when facing agents of unknown types, the principal may want to distort some of the transactions to meet the incentive constraints. Okay, so that's it for today. Right, bye.